In this video, I will show you that the one-dimensional particle in the box obeys Heisenberg Uncertainty Principle. The wave function of the one-dimensional particle in the box with a infinite energy barrier is the square root of 2 over a times sine n pi x over a. The square root of 2 over a is the normalization factor. We now compute the uncertainty of the position and the uncertainty of momentum separately for the particle in the ground state. The uncertainty of the position is given by the square root of the expectation value of x squared minus the average value of x squared using quantum mechanical postulate 4. So over here we have the expectation value of x squared. And then we have psi star, the complex conjugate of the wave function, and multiplied by x squared, multiplied by the wave function, and on the bottom we should have the squared modulus of the wave function. And because the wave function of the particle in the box is already normalized, the value of the bottom integral is 1. So it's a bit difficult to evaluate the integral on the top. It can be simplified as 2 over a times the integral from 0 to a of x squared times sine pi x over a squared. So I used Wolfram alpha to get the value of this integral, which is actually 1 over 12 times 2 minus 3 divided by pi squared a to the power of 3. And then this 2 over a is the normalization factor squared. So I put everything together, I got 0.282673 a squared. That's the expectation value of x squared. And due to the symmetry of the wave function, we know the average value of x is 1/2 of a. So we can simply compute the uncertainty of the position using this equation. We plug in these numbers. This is from here, the expectation value of x squared. Over here, this is just 1/2 of a squared. So we get the uncertainty of the position, 0.18 times the length of the box. Now we compute the uncertainty of the momentum. We use a similar equation here. And the value of p squared is actually definite. So it's simply p squared. And p squared is equal to 2me. It's because we have 0 potential energy in the box, so this E is equal to the kinetic energy of the particle. And then we know the expression of the energy of the particle, which is n squared h squared over 8ma squared. So we use that, multiply by 2m, we get n squared h squared over 4a squared. Or we can use quantum mechanical postulate 4 again to compute this expectation value of p squared by evaluating these two integrals. Again, on the bottom, this integral is 1 because the wave function is already normalized. On top, we use this momentum operator twice being applied to this wave function. And the result is n squared h squared over 4a squared again. And because the wave function can be expressed as a linear combination of two eigenfunctions of the momentum operator, e to the power of plus ikx and e to the power of minus ikx, and k is n pi over a, so we can actually compute the ratio of the probability of finding the particle moving forward versus backward, and the ratio is exactly 1. How do we get this? We simply just need to get the squared modulus of the coefficient in front of this e to the power of plus ikx and divide that by the squared modulus of the coefficient in front of this second eigenfunction of the momentum operator. And then we have this equation here. How do we evaluate the squared modulus of a complex number? It's very simple. The squared modulus of a complex number is that complex number multiplied by the complex conjugate of that number. How do we get the complex conjugate? We simply replace every single I with negative I. So that's what I did here. And similarly, on the bottom, I have this squared modulus of a complex number. Therefore, I'm copying this number here, and then I replace this I with negative I. And on top, you will see the product is 1 over 2a. On the bottom, you will see the product is also 1 over 2a. So the ratio is 1. What does that mean? That means, well, we have 50% probability of finding the momentum of kh bar, and also 50% of probability of finding the momentum of the particle being negative kh bar. So 50 plus kh bar, 50 negative kh bar. Therefore, the expectation value of the momentum is 0. And then we can compute the uncertainty of the momentum using this equation again, and the average momentum is 0. Therefore, we have just simply the square root of p squared here, which is nh over 2a. And this is very general for n equals 1, 2, 3, and so on. For the ground state, n equals 1. Therefore, for the ground state, the uncertainty of the momentum is h over 2a. The uncertainty of the position is 0.18a. And then the product of delta x and delta p is over here h over 2a. That's the uncertainty of the momentum. Over here, this is the uncertainty of the position. The result is 0.09h, which is greater than 1/2 h bar. So here's just a reminder of the Heisenberg Uncertainty Principle. The uncertainty of the position times the uncertainty of momentum should be greater than 1/2 of h bar. H bar is h over 2 pi. Therefore, this is equal to h over 4 pi, which is 0.07958h. Again, this number is the product of the uncertainty of position and the uncertainty of momentum of the particle in the box. And this number is greater than 1/2 h bar.